Right, gentlemen, this screencast is about writing half equations in acidic conditions. We've already looked at half equations more generally speaking, but half equations in acidic conditions require you to approach the writing of the equation in a particular way. And then combining half equations together leads you to produce an overall equation which can be quite different to the initial half equations or fragments of half equations that you're given. So let's just run through the procedure and hopefully it'll all make a little bit more sense. So there are many equations which require acidified agents in order for redox reactions to occur. So if you look at this piece of information, we've got sodium dichromate being added to nitrous acid, which is HNO2, and the dichromate dissolves and it forms a dichromate ion. The dichromate ion, it says, is converted to chromium 3, and the nitrous acid is converted to the nitrate ion. This asks you to write half equations to show this naming, which is the oxidation and reduction half equations. So if we look at the first step for writing half equations in acidic conditions, we have to balance atoms first. So if you look at this dichromate ion over here, you can see we've got 2 chromium atoms in there. On the other side, we have just the 1 chromium atom in the information that we're initially given. So we need to make sure that they balance. Okay, so we're just going to look at the common element on each side of the equation for now that can have a variable oxidation number. So chromium in this example would be the 1, and in the bottom example the nitrogen. How do we know which one's going to have a variable oxidation number? Well, the oxidation number rules, if it's not specified in those, then they can be variable. So once we've balanced those particular atoms, then what we need to do next is we need to address the fact that there's oxygen here but there's not on the other side. And in this case there's oxygen here, there's 2 of them, but on this side there's 3. So clearly we need to add in some oxygen to try and balance the equation. So if we do that, you can see that by adding in water, we add in oxygen. All right, so we need to add in water because water is, all of these are aqueous. And step 2 of any procedure, we add in water molecules to balance the oxygen atoms which aren't or appear to have disappeared. Whoops. So once we do that, we create another problem having solved one. So you can see here that I've now got 14 hydrogen atoms on this side but none on the other side, and I've got 2 hydrogen atoms plus this one, which makes 3, but none on the other side. So there's too many hydrogen atoms. So because we're in acidic conditions, we can add the H plus ion to remedy that situation. So that is step 3 of this procedure. So if I add in 14H plus over here, that balances my 7H2O over here, and then 3 hydrogens ions here, that balances 1, 2, 3 here. But if we now look, we can see that the charges don't balance for each of these half equations. So we've got -2 here, 14 positive here, so that's plus 12 on this side. We've only got plus 6 on this side. And similarly, in the bottom example, I've got plus 2 on this side, and I've got 0 on this side. So the charges don't balance, which means that electrons have blinked out of existence or into existence in each of those half equations, and that doesn't happen. So we have to add those electrons in to make sure that the charges balance on each side, and therefore the number of electrons is consistent on each side. So that's the next step. So you can see here, this is how I've calculated what the charge is, -2 plus 14, so there's plus 12 on this side, and on this side, 2 lots of plus 3, that's 6. So if I add 6 electrons to the most positive side, which is this side, then I'm going to end up with the correct charges on each side, which are plus 6. I do likewise for the other one. So you can see here there's no charge. On this side there's plus 2. So if I add 2 electrons on this side, this means that this side also equals 0 and the charges balance. So these are the final half equations. Cr2O7 plus 14H plus 6 electrons gives you 2 chromium 3s plus 7 waters, and the oxidation half equation HNO2 plus H2O gives the nitrate ion plus 3H plus 2 electrons. So how do I know this is the reduction half equation? Reduction is gain of electrons, so the electrons appear on the left-hand side because they're being added into this, and the oxidation is lost, so therefore they appear on the other. Now, to produce an overall equation, we have to add the half equations together. And what the name of the game here is, we want electrons to not appear at all in the final equation. So if we look at the two half equations, you can see we've got 6 electrons here, and then in blue, that was the original half equation that we ended up with after the first part of the procedure. Then the 2 electrons here don't actually cancel out with the 6 electrons over here. What we want is the same number of electrons on both sides. So for this half equation here, if I multiply it up by 3, we then end up with 6 electrons. So if I multiply by 3, I end up with 3 of the nitrous acid, 3 waters, 3 nitrate ions, 9 H+, and then 6 electrons. I can then add everything together and then do some cancelling. So that's what I end up with. The electrons cancel. All right, so we can get rid of those. The 7 waters, because we've got 3 waters over here, I take 3 of those away, so I end up with 4 waters on this side. I have 14H plus over here, and I have 9 over here. So 14 take away 9, I end up with 5H plus. And that's everything that cancels, so I end up with this as my final overall equation. And that is basically how you produce overall equations which are fully balanced in acidic conditions and create half equations in acidic conditions. That is all there is to it.